Welcome, everyone. I'm Ari from OpenSciEd, and I'm here to introduce you to Unit 6.3, the Weather Unit. In the science storyline approach used in OpenSciEd, the sequence of activities is designed to make sense to students. These storylines were developed based on the input from hundreds of classrooms and the questions students actually asked. So let's dig in and see how the story of Unit 6.3 unfolds. OpenSciEd units are organized into collections of lessons called lesson sets. A lesson set is just a group of lessons that is focused on figuring out a part of our phenomenon. At the end of a lesson set, students put their ideas together to explain what they can at that point. The weather unit has 4 lesson sets. Lesson set 1 contains 6 lessons, which help students answer the question about weather conditions and what the air is like outside when hail occurs. Lesson set 2 takes us through lesson number 13, which helps students think more about water and moisture in the atmosphere. By the end of this lesson set, students answer the question about why do some clouds produce precipitation while others do not. During lesson set 3, students think about the atmosphere as a system and examine weather map data to help answer the question about what causes large-scale precipitation events and how we can predict them. And finally, during lesson set 4, students analyze global weather events over longer time periods to help answer the question about why some places tend to get more precipitation than others when observed over time. Keeping in mind the unit driving question and how each lesson set addresses different aspects of that question, let's look more closely at the lessons themselves. First, we'll take a closer look at lesson set 1 of Unit 6.3. In lesson 1, our anchor, we watch several videos of hail events, and we develop an initial explanation about what causes this to occur. We also identify related phenomena, we generate a driving question board, and brainstorm ways to investigate our questions. In the end, we figure out that rain and wind accompany hail events, that some of the water freezes before it reaches the ground, and that clouds are visible during all these hail events. We had questions about what the conditions or weather was like on these days when it hailed. So in lesson 2, we interpret data from several hail events to identify weather patterns that may help us explain why hail forms at those locations. We figure out that hail is more common in the central United States. On days when it hails, there is relatively warm temperature and high humidity, so usually not in the winter. And hailstorms appear later in the day and during the fall, spring, and summer, again, not during the winter. From lesson 2, we know it's typically warm when it hails. So we're left wondering, how does water freeze to form hail if it's so warm outside? So in lesson 3, we analyze data from weather balloon satellites at varying altitudes in the atmosphere at different times of the year. We figure out that regardless of season, the air is always colder at higher altitudes. In fact, cold enough to freeze water. And by connecting this with what we know from the thermal energy unit with thermal cups, we know that the speed of the air molecules is slower at higher altitudes where it's colder. Now that we know more about the air really high up in the atmosphere, we want to know why the air just above the ground is always just a little warmer than the air at higher altitudes. So in lesson 4, we examine several different types of ground surfaces, and we measure the temperature differences at varying heights near the surface, while also measuring the amount of sunlight reflected off of those different surfaces. And we find out that energy from the sun is absorbed by the ground, which increases the kinetic energy of the particles in the ground, that different surfaces heat up differently, depending on how energy from the sun is absorbed, and that as air particles contact the ground, energy is transferred to those particles, thus warming up the air right above the ground. So in lesson 4, we figured out energy is transferred from the ground to the air through conduction. So now we're wondering what happens to the air after that. After 2 investigations during lesson 5, in which we closely examine the air in contact with the ground, we figure out that warmer air is less dense than cooler air and tends to rise. Then, once it rises, air cools. It becomes more dense and sinks back down towards the ground. So next, we take what we figured out about the air movement and try to explain how air moves in a hailstorm cloud in lesson 6. After watching a video of cloud formation, we think we have all the pieces we need to explain that air near the ground is warmed, becomes less dense, and rises high above the ground. Eventually, that air cools as it gets higher, becomes more dense, and begins to sink back down to the ground. And based on weather map data, we also know this movement happens more on sunny days since the ground heats up more when there's more sunlight. But we're still wondering, why is it so humid when it hails? And where is this water in the air actually coming from? Which leads us to the second lesson set. Now we'll look closely at lesson set 2 of unit 6.3. We begin the next lesson set with lesson number 7, in which we design a bottle system that incorporates humidity probes to investigate where the water in the air is actually coming from. We figure out that when water particles on surfaces gain enough energy, they leave the liquid form and become a gas through evaporation. Now we're wondering what happens to the water in the air as the air rises up and eventually cools. So in lesson 8, by cooling the top of a water bottle with an ice pack, we notice that the water present in cooler, denser air starts to clump up and condense into liquid form. We then use marbles to model the mutual attraction between water molecules and how changes in their speed cause water to change from gas to liquid when it cools below a certain temperature. So now we're left wondering, why aren't water droplets always forming in the air? What's happening to the water in the clouds above us on any given day? In lesson 9, we use the bottle system once again, this time containing some hot water and topped with an ice pack. Using this setup, we see how clouds form from the condensation of water vapor. Additionally, from a reading, we learned that condensation requires a surface, such as dust, for water particles to actually stick to. And if the water rises up high enough to where the temperature is very cold, high in the atmosphere, the water droplets that condense can actually freeze into ice crystals if there is something for them to stick to. So now we're wondering why clouds aren't always forming in the sky. So in lesson 10, with the aid of a simulation, we figure out that stronger storms tend to happen when there's a bigger difference between temperatures near the ground and temperatures higher in the atmosphere, and when there is higher humidity. The simulation also shows that in bigger storms, the clouds tend to grow taller into the sky, which leads us to wonder whether that has something to do with whether hail forms or not. But we're still wondering why water or ice isn't falling from the sky all the time. So in lesson 11, students conduct several investigations to examine how wind can counteract gravity to keep certain particles suspended in the air for longer until they collect more water particles, liquid or ice, and their weight becomes too great and they fall back down to the ground. As part of the investigations in this lesson, students are introduced to air pressure and are wondering whether the changes in air pressure also have something to do with whether clouds form and with precipitation. In lesson 12, we use water as a way to investigate how fluids behave as a model for how air behaves under different conditions. After adding dye to the water and a heat source, we notice that warm water rises while cool water sinks. And more importantly, we see this circular convection current even more clearly when more thermal energy is put into the system. As the warmer, less dense air rises, more air rushes in to take its place, and we get wind formation. We connect this to our earlier understanding that the Earth's surface heats due to energy from the sun. And we figure out that bigger clouds holding more water form when heating from the Earth's surface is greater, so when air temperatures are warmer. By lesson 13, we've now figured out enough to explain that storms in which there are really strong updrafts of air can keep water particles up longer and help them travel higher into the atmosphere where it's colder. The longer the particles are kept in the air, and the more often they travel to high altitudes, the larger the hailstones can eventually become. Also during this lesson, there's a transfer task in which students use everything they figured out and apply it to explain what causes hurricanes to grow in size and produce strong winds with lots of precipitation. Now we'll take a look at lesson set 3 of unit 6.3, but we'll do this more quickly. The previous lesson finishes with students thinking about hurricanes And so this lesson set has students looking closely at large-scale precipitation events as opposed to short-term ones like hailstorms. In Lesson 14, students explore maps and videos and notice that storms can vary greatly in size, in duration, and amounts of precipitation that falls. In Lesson 15, students examine whether the types of storms are related to the movement of warm and cool air across the country. Students find out about air masses and figure out that they can be enormous, that they tend to move from west to east across the United States, and that storms occur when two air masses with different characteristics meet. In Lesson 16, students investigate what happens as warm and cold air masses collide. We figure out that typically warm air moves over cold air, and predictable amounts of precipitation result. However, students are still wondering how scientists can predict when air masses will collide. In Lesson 17, students explore national pressure maps and notice that air masses tend to move in predictable ways, and they correspond to patterns in changing air pressure. And that precipitation tends to occur in areas of low pressure where cold and warm fronts collide. And finally, in Lesson 18, we again put together all the pieces to explain what was happening in one part of the country at one point in time can actually be connected to what is predicted to happen in another part of the country a day later. And finally, Lesson Set 4 of Unit 6.3, again, more quickly. The previous lesson finishes with looking closely at large-scale precipitation events and how predictable they are, which takes us into the final lesson set, where students explore whether there are geographical patterns to the weather we experience. In Lesson 19, students use visualizations of precipitation patterns across the United States to figure out that air movement and precipitation patterns typically align, and there are prevailing winds that move mostly west to east that moves precipitation in the same direction. Students begin to notice patterns of repeating weather in specific locations over long periods of time, meaning they can now differentiate between weather and climate. In Lesson 20, students gather information about how oceans affect local weather patterns and figure out that the ocean is warmer near the equator, that ocean currents bring warm water towards the poles, that more evaporation of water occurs near the equator, and that temperature of the ocean affects the humidity of the air moving over it. In Lesson 21, students investigate why the Pacific coast and the Gulf Coast are affected differently by their neighboring ocean. We figure out that changes in elevation affect how air moves over land, and that as elevation increases near the Pacific coast, air is forced upward, it cools, and loses most of its water. Alternatively, near the Gulf Coast, the moist air travels far inland because there is little elevation change in the southeastern United States. Using everything we know about weather and climate patterns, students now try to explain climate patterns outside the United States. In Lesson 22, students use what they figured out to explain why rainforests in South America are located where they are. So that's the journey students take in Unit 6.3, the Weather Unit. It isn't just about figuring out why hail sometimes falls from the sky. It's about helping students grow as modelers, as questioners, and as collaborative thinkers. So follow the story, build on their questions, and get ready for some real light bulb moments.